So let's get started with another chapter, Large Eddy Simulations. Large Eddy Simulation, also called LES. Okay, so now here first we have to recall, as I told you, this Kolmogorov hypothesis has a lot of advantages for turbulence modeling community. One of the big advantage we see it in the so-called LES modeling. So what is this Kolmogorov hypothesis? If we quickly recollect, if you recall the Kolmogorov hypothesis, or the so-called K41 theory. So we had this very energetic eddies, right? The large integral scale, and then we have the tinier ones. Let's say the intermediate scales, and then finally some dissipative eddies. So this is the cascade image that we also discussed. That is the energy cascade. So what we discussed there is that in the Kolmogorov hypothesis, it is considered that the large eddies, the integral eddies, are the places where energy injection occurs. These are the energy containing eddies, right? So the energy injection occurs at these, you can say, energetic eddies. Okay, the injection of energy occurs at these large scales according to the cascade process or the Kolmogorov theory, and we do have this dissipative eddies. And of course the intermediate ones, which is the inertial subrange, right? Inertial range, where it's purely inertia driven. So the main advantage of this Kolmogorov hypothesis in the context of LES is, we discussed that there exists these tiny scales where it is statistically isotropic, right? So local isotropy or statistically isotropic at small scales. This has a profound impact in LES. So the idea here is that as against direct numerical simulations where you need to capture all the scales of turbulence, right? In DNS, all scales of turbulence must be captured. All scales of turbulence must be captured, computed using your temporal and spatial grid. Now in LES, the idea is that if this so-called tiny scales, tiny eddies or dissipative eddies, if there is a local isotropy at these dissipative eddies, why not take advantage of that? You know, if there is a local isotropy at these scales and it is not defined what kind of flows there, right? At every high Reynolds number flows in a fully turbulent flow, there exist small scales where dissipation is occurring, and it's universal according to Kolmogorov hypothesis. So I can make a universal model, right? So one challenge in the DNS was that the scale separation, right? So the eta was so tiny, you have to resolve the here you had to capture the Kolmogorov microscales. you have to capture. Okay, you have to capture Kolmogorov microscales. That means essentially you are capturing these dissipative eddies. But if it is locally isotropic, then I can introduce a model so that the mesh size that I am going to use is not eta, but much larger than eta, maybe 10 times, 100 times than eta, right? So then I will resolve not up to here, but for example, if I say this will be the entire spectrum, like this will be the entire DNS spectrum here, which is going to capture from the largest to the tiniest, right? So everything is being captured. In LES, we don't do that. What we do in LES is that we only look at, we will have a mesh. This is resolved, and the rest part here is modeled. Okay, so in LES, this is what we call resolved or captured using your mesh, computed, right? You can say computed, and this is modeled. So the tiniest scales are modeled. Since it is statistically isotropic, universal in behavior according to Kolmogorov hypothesis, we take advantage of that. So this is the general idea behind LES. Of course, in RANS, you are not capturing any of this. Everything is modeled here. No eddy was captured using your numerical mesh there. It is statistical, you are only computing the mean flow. Here, as you see, even though I have written, it has come out to be a little bit random. If you see the large eddy or any of this, it is slightly looking different, right? So that random component is being captured here using LES or DNS. It's just that DNS would capture all the scales. In LES, depending on your mesh size, you would capture mostly the large eddies, and that's how the name came here, the large eddy, because you are capturing the large scales by modeling the small scales. Okay, so in LES, large scales are computed. Okay, the small scales are, that is dissipative eddies, small scales are modeled, taking advantage of this local isotropy assumption. So no need to resolve all the way to Kolmogorov. So we'll come to grid guidelines later, what we do at LES. So now we have to compare between RANS and LES to proceed. Okay, a quick comparison here is that, let's say, so comparing RANS and LES, comparing RANS and LES. So in RANS, what we did is Reynolds decomposition and averaging, right? So in RANS, we did Reynolds decomposition and ensemble averaging. So what does that mean symbolically is, if I have phi, a random component, I am going to decompose it into phi bar plus phi prime. Here the phi is the random component, a random signal, phi prime is random, and phi bar is statistical. The mean, right? So the randomness has been separated, split out, and then statistical part is what you are focusing. And in RANS, of course, you modeled this part. This is modeled. This is computed. Statistical part is computed. In LES, this is slightly different. in LES, if I have the same components here, let's say phi, I write this as phi bar plus phi double prime. I'm going to use double prime here. Okay, it has a different meaning. So here all three are random. Okay, all the three components are random. Why? Then what is this meaning of phi bar here? Here over bar, okay, here over bar, this symbol represents volume averaging or low pass filtering. Here over bar means low pass filtering or volume averaging. This is different compared to the ensemble averaging, right? So this phi bar here means ensemble average, right? So here over bar means ensemble average, this part here in runs. So here over bar, whenever I write over bar in LES chapter, it means low pass filtering or volume averaging, not your ensemble averaging. Okay, so now let's see what this actually means, this phi bar and phi double prime then. Okay, so now I have this phi bar component. This is usually called filtered component, sometimes also referred to as resolved or resolved component. Even though these two has a different meaning, but interchangeably people use it. Colloquially they use filtered or resolved, but it has a different meaning. I'll explain why it is different. And the phi double prime, phi prime prime, so this means residual component or subgrid scale component. Subgrid scale, SGS component. Again here these two are used interchangeably, okay, but they have a different meaning. Filtered versus resolved, residual versus subgrid scale has a different meaning to it, okay. And over bar, as I said, always means filtering operation. So to understand it, let's take an example of what does it come to your head when I talk about filter? Coffee, right? Okay, or tea, whatever you are going to do, or juice since it's summer. So let's take up this example of, let's say you have a coffee filter. Okay, so let's say I have this coffee filter here. It has mesh, right, to capture whatever you want to capture. So this is your coffee filter mesh, right? And this is just for your understanding. So now you are going to pour your coffee or whatever, the coffee beans powder and hot water and everything. So you do get certain things here collected. Some things are getting collected and some things come out of it. What is residue here in the context of coffee? What you have captured inside the mesh, this red symbols that I have drawn, right? That is your residue, that is useless. You are not going to eat that, right? You are going to drink this green dots, that is the coffee droplets. It is opposite here. Filtered means what you are capturing by your filter. Let's have a numerical mesh. What can it capture? It can capture eddies, vortices that are larger than the numerical mesh. If your numerical mesh is, let's say, 1 millimeter cube, you cannot calculate or capture vortices or eddies which is, let's say, 10 micrometer cube, right? So obviously the eddies that are larger than the mesh size is only you can capture. So what is useful here for us is what is being captured. So this red is your filtered component, okay, in the context of LES. So this red part here is filtered component, right? The eddies that you are capturing, right? So turbulent eddies being captured by mesh, the LES mesh that you have used, and this the so-called green droplets that is coming out of the mesh, that is a residue. This residue is what is being not captured in LES, okay? So this is your residue, what is coming out of it, okay? So now if you have access to these two things, okay, the filtered as well as residue, then both are exact. Let's say I have a DNS data and I use an LES filter. I'll tell you what the filtering operation is, but let's assume that you have a DNS data and then you are doing filtering operation alone, okay? So let's say you have as I said 10 micrometer mesh, you calculate DNS on that, and now you move to 1 millimeter mesh. On that new mesh you are going to filter the DNS data, okay? So then you have the residue that is coming out. That means you have this the phi in LES is phi bar plus phi double prime, right? So if phi is the DNS data and I am doing a filtering operation phi bar, then phi double prime, the residue, is exact. You have access to this. You can subtract the DNS data minus filtered DNS data to get residue, right? So for example, if this is phi DNS, this is phi bar DNS filter, or you can say filtered DNS data, then this is the exact residue. Phi double prime, you have access to it. But in LES, as I told you, this residue, that is the tiny eddies that is not being captured by your mesh, is modeled. You have no, just like RANs, you have no access to the tiny eddies, these green vortices, no access to that. You are modeling them. So obviously phi double prime is unknown in LES. You have access only to the phi bar in LES, which is LES resolved. That's the name between the difference between filtered and resolved. So in LES you will have, I can write here, phi will be phi bar plus phi double prime. So then this particular component will be your LES resolved, captured by your LES mesh, okay? In LES mesh is used here. This is that is what it is able to capture, and phi bar is unknown, okay? So this is called subgrid scale. So this is your unknown. That is, the name subgrid itself explains the vortices that are subgrid scale smaller than the grid size, right? Subgrid scale. This is to be modeled, okay? To be modeled in LES. So phi double prime is modeled component, but phi double prime, if you do filtering operation on a DNS data, is exact. So these two are different. That's why the name filtered and resolved are different. But people do use it interchangeably, filtering and resolving. You understand, right? you have a DNS data, you can filter it out to get exact residue. But if you use the same filter size as your mesh size and run LES calculation, then you would get a filtered, or you can say, sorry, not filtered, you will get a resolved data. Whatever you are resolving is capturing on that particular filter size or mesh. Then the residue you have no access, it will become unknowns, and you need to model this. Okay, so I'll show you an example, then it becomes little more clear.